So a couple announcements. Homework 4 is due next Wednesday. So of course, no homework due today. I sent that announcement out. So Wednesday, October 7th, homework 4 due. I will post the subsequent homework due dates shortly. I want to get them synchronized with the lab and the class. Pre-lab 4, don't forget that's due this Thursday, and you will start your lab on Friday, so that will be lab 4. So take a look at that. My office hours will be right after class, and TA's office hours are posted along with their Zoom links. And if you have any questions, unmute. Otherwise, please stay muted to keep the background noise low.
No quiz this week?
No quiz this week. So what I wanted to do was start out by finishing up the more complex RL circuit example that we had started last time. So let me bring up my whiteboard here. Okay, so you should be seeing my whiteboard now. This is roughly where we left off. So we had this circuit. It had 2 resistors and an inductor, and the switch opened up at t equals 0. So this 6 ohm resistor went from a shorted resistor to a resistor actually being in the circuit when it got unshorted at t equals 0. And I'm approaching this problem using the initial and final or steady state value approach. And what we did last time is we looked at the circuit before t equals 0, and we said this switch had been closed for a long time before t equals 0, so we assumed it was at steady state. Then at t equals 0, the switch opens up, and a transient response happens, and that current changes, the current through the inductor. And we found the steady state response long after the switch had opened up and figured out these 2 values. So the initial value for the current was 24 amps. The final value or steady state value was 16 amps. And so now the question is, well, how do we find the time constant, tau? And we didn't work this problem, but I told you, and I showed you on a slide last time, that if you did work this circuit at the bottom left using KCL, KVL, and differential equations, you would find out that the response has a time constant of L over R, okay? But we don't really know which R to use in the circuit above. We have 2 resistors in the circuit connected to an inductor, so this doesn't help us too much, well, yet. So this is where we're going to leverage our work on Thevenin equivalence. If I draw a couple terminals here, this circuit looks like an inductor connected to a Thevenin equivalent of a circuit. If I draw the corresponding points next to the inductor on the original circuit, what I need to do is figure out the Thevenin equivalent to the left of those terminals for t greater than 0. That's the response we're trying to find, the response after t equals 0. So let's do that. Let's redraw the circuit briefly for t greater than or equal to 0. And I'm going to leave off the inductor because what I'm trying to find, in fact, I'll color those terminals red. What I'm trying to find is the Thevenin equivalent of that circuit.
Should it be 24 amps?
Yeah, no, yes, it should be. Thank you. Thank you very much. I confused myself by drawing a current source here, or a voltage source instead of a current source. Okay, so we have 24 amps, 24 amps. Yes, Now we should be right here. Now, the Thevenin equivalent still has a voltage source. What we want to do is figure out what the Thevenin resistance is of this circuit in the upper right in order to figure out that resistor value that we will use in L over R. The Thevenin voltage, it turns out, isn't needed here. I already have the current values that I need, the initial current and the final current. I'm really just looking for the Thevenin resistance of the circuit so I can fill in that R value. Okay, let's pretend we're just starting out with figuring out the Thevenin resistance of the circuit. So remember, to figure out Thevenin resistance, if you have only independent sources, you can zero out your sources, meaning that's 0 amps here. This is still 12 ohms. This is still 6 ohms. Okay, so, and I'm looking into these terminals or measuring between those terminals and figuring out Req, which equals my Thevenin resistance. And you can see that the 6 ohm and the 12 ohm resistors are in series. So 6 plus 12 equals 18 ohms. Okay, so that's my value that I'm going to use in this model that uses L over R. So I can figure out tau. So that's going to be 0.1 over 18 ohms, which, if you calculate that, it's 0.0056 seconds. Okay, or let me write it this way, 1 over 180, because you'll see we have a 1 over tau in our expression in the exponential. So finally, now that I have tau, I can say from this equation, I of t equals, let's see, I final plus I initial minus I final e to the minus t over, well, 1 over 180, right? And so let me clean that up a bit. Okay, so the point here is that you can use the initial and steady state value approach, and you need to find 3 terms. It's usually pretty easy to find the initial and the final value for either voltage or current. But then you have to decide, well, what resistor do you use for L over R? And the answer is you have to get the circuit into the form with a series resistor, with the series inductor, and that can be done with the Thevenin equivalent circuit. Okay, any questions on that? Okay, so let's summarize first order circuits. So, takeaways from this section. We talked about a transient response of a first order circuit, and that's a change in voltage or current after a sudden change happens, after a step change happens. And it consists of an initial value, an exponential change, and a steady state or final value, right? So you can see that graph here in the upper right. The time duration of the exponential change is characterized by or using or described by a time constant. And once you've reached about 5 time constants, we say that steady state or the final value has been reached. You're within 1% of your final value. And then in steady state, you can analyze a circuit by replacing the capacitors with opens and replacing the inductors with shorts, because all of the values of voltage and current are DC, and that way that derivative in their current versus voltage equation goes to 0. Okay, finally, you can use the steady state information as well as the time constant to figure out what the transient response of the circuit is, what that exponential rise or exponential fall is, by using the initial value, final value, and time constant. Okay, any questions on that?
Professor,
Yes.
is there a sort of like physical standard as to whether that is an exponential growth or decay, or
Well, yeah, it's just simply that if the initial value is higher than the final value, it's going to be an exponential decay. And if the initial value is lower than the higher value, if the initial value is lower than the final value, then it's going to be an exponential rise.
okay, so it just depends on the circuit itself?
It does.
Okay.
It does. Okay. So I'd like to bring up the course roadmap because we've reached another milestone. We've just finished up transient circuit analysis, RC circuits. And so we're coming to the end of the circuits part of the course. We're going to finish that up with analysis of AC circuits. So circuits that have mostly sinusoids. We're going to look at sinusoidal currents and voltages. If you've studied Fourier analysis, then you know that any periodic waveform can be made up of sinusoids. So if you can solve a circuit for sinusoids, then you can solve a circuit for any waveform. So let's take a look at that. So let's talk sinusoids. So I clear off our transient response material. So a sinusoid is a sine wave. It's a sine or a cosine. We're going to use the cosine function, and I'll show you why. So a sinusoidal voltage would look like this. This is probably review, but what I want to do is define some terms, define some parameters of the sinusoid so that we can speak a common language here. So I've written V of t equals Vm cosine omega t plus theta. And so t is a time variable, and this is a description of a, well, sine wave or cosine. They have the same shape, except they're phase shifted. V sub m we're going to call the peak value. And the peak value is in units of volts. Omega is a frequency term, and we're going to call that the angular frequency. And that term is in radians per second. And then we have theta. Theta is a phase term. And that is in that has the unit of radians. Okay, so any argument of a cosine, typically, or a sine, is a unit of radians. We can switch to degrees, but you have to be consistent with your units. So those are the terms we're going to use to describe a sinusoid. Let's draw this out. So that's v of t there versus time. And so cosine, which is meant to be a maximum right there, if the cosine has a 0 phase term, then its maximum falls right at time equals 0 there. And that maximum is the value of v sub m. The minimum occurs down here. That would be minus v sub m. So the peak to peak value from one peak to another peak is 2 v sub m. The frequency defines how rapidly this wave transitions versus time from high to low. And we're going to define a term called the period. That's in seconds. And period relates to frequency by the inverse. So frequency is 1 over t. And this frequency is in hertz. Okay, or cycles per second. Okay, you can think of this as cycles per second. I'm calling the F term just frequency and the omega term angular frequency. You can call them both frequency. You just have to understand that when you're working with omega, you're working in radians per second. When you're working in with F, you're working in cycles per second or hertz. The relationship there is, well, there's 2 pi radians per cycle. So you can convert cycles per second to radians per second. Omega equals 2 pi F. Okay, so those are the terms we're going to use generally for a sinusoid. There's one other term that is actually very practical, and it's the RMS value. Okay, this is also called the effective value. And let me show you what it means before I tell you the formula for it. It means this. Let's compare a DC source to an AC source and its ability to deliver power to a resistor. So let's take a source. Let's call it VDC. It's a constant value. Let me make up a number. Let's say it's 10 volts. It's a 10 volt DC source, and I have a resistor of some value, R. It's constant value. And then I take an AC source, and I'm going to label that V of t, maybe VAC, V sub AC of t, and it looks like a sine wave versus time. And I take that source and I connect it to the same resistor. Let's call it R1, it's a value. Let's suppose that I want to deliver the same amount of power to the R1 on the right as I do to the R1 on the left. Right? So the R1 on the left has a value of 10 volts. The question is, well, what peak value do I assign to that VAC, that sinusoid, in order to deliver the same amount of power? And the answer is this: you would like an effective value, or equivalently an RMS value, of 10 volts. You know that the power for a resistor is V squared over R. So you can actually use 10 squared over R1, or here 10 squared over R1. We just have to use the effective voltage, the effective value of that AC voltage, when we do the power calculation. So as you would expect, the effective value is the RMS value, the root of the mean of the square. Okay, so I'm going to take the root, square root, of the mean. To take a mean, you integrate over one period of a periodic waveform, and you divide it by the period itself. So the root of the mean of the square, let me write that a little more cleanly. Okay, so that is the RMS value, the root of the mean of the square. That's a big takeaway here. And you can do that calculation for a sinusoid. And what you would find is that for every sinusoid of any frequency in any phase, that VRMS equals Vm over square root of 2. So if you have a triangular wave or some other waveform that doesn't count, this is only for a sinusoid. Okay, so if I have an RMS value of 10 volts, meaning this RMS value is 10 volts, I multiply that by root 2, I get Vm. If I place Vm here in the sinusoidal value for this source, the resistor R1 on the right would get just as hot. It would get the same amount of power delivered as the resistor on the left, the R1 on the left. So there's a practical part of this. When you probably know that for residential power in the United States, the voltage is 120 volts. What some folks don't know is that's actually 120 volts RMS. So you can put a unit, volts RMS, if you want. And so what that means is that if you were to take an oscilloscope, I recommend not doing this, and plug it into the wall, again, I recommend not doing this, you would see that the peak value of the sinusoid, V sub m, is actually root 2 times 120, and that's 177 volts. So that 120 volts isn't the peak value of a sinusoid. If you were to measure it coming out of your wall, don't do that. It's 177 volts. Okay, so that's a value of RMS. It describes how much power, or it describes a voltage to use while calculating power delivered to a resistive load.
Professor?
Question.
Yes.
So in the more complex form of the VRMS, like the original form you have there, why is it that we take the integral from 0 to whatever the period value is?
Oh yeah, okay. So if you're, and this is true for any waveform, let me just draw, like, for example, a triangular waveform like this. For any waveform, if you want the average of a waveform, you can draw any point in time, draw a line at any point in time, and then one period later, you can draw another point in time. And if you want the average, you integrate over that duration and you multiply by 1 over t. Okay, that's true for even, well, if you want to take the average of even a DC value between 2 points in time, you can do that. So that's the equation for calculating an average of a periodic waveform is 1 over t times the integral of one period. Okay.
Quick question.
Yeah.
Why exactly don't you want to plug an oscilloscope into your electrical outlet? Is it for the same reason you don't want to put a fork in there?
yeah, because you want to make sure you know what you're doing, and the problem is that it's not safe. And the reason it's not safe is because, well, you're exposing the terminals of 120 volts, which can kill you, and that's not safe. And also, if you plug an oscilloscope, one side of an oscilloscope, one terminal of the probe of an oscilloscope is often connected to earth ground, AC ground through the power outlet. And so if you connect the ground of the oscilloscope to what's normally called the hot wire of AC, you're actually creating a short to ground, and something's going to give. You'll probably burn up your probe, and it's probably going to light up and catch fire. So that's why I recommend not doing it.
All right.
Yeah.
Good to know.
Yeah. And if you do it with your AD2 and it burns up, it costs you another $200. So there's another motivator there.
Professor?
Yes.
This is going back to the equation, but then, so why is v of t squared within that integral?
Yeah. Let's see. The squared comes from the RMS value. So you're trying to take the root of the mean of the square. So I guess if you want to talk about why RMS is the effective value and why that works, let's take that offline. But basically, the RMS value, and this is sort of a hand wavy, trust me, RMS value is the effective value because it describes the voltage that you need to use in V squared over R to calculate the power.
Okay.
Right, so you have to use the RMS to calculate power in V squared over R, and RMS is described by the root of the mean, that's the integral with the 1 over t, of the square of your voltage.
Okay, gotcha.
And if you look at, if I were to take the average of a sine wave, let me just draw it on here. If I take the average between those two blue lines, the average is 0. But we know that if you connect this waveform across a resistor, it's going to heat up. The average power is not 0.
Okay. Oh, so VRMS is that voltage that you use within the power equation when you're dealing with an AC circuit?
It is.
Okay, gotcha.
It is, yes. So effectively, it's like you're connecting a DC source of that power to a resistor. So P equals VRMS squared over R.
Is it in all situations okay to use the DC analogy?
If it's a resistive circuit. Do you mean, is it okay to always use the DC analogy? So it's always okay if you have a resistive circuit. In other words, there's no capacitors or inductors in there that do some funny things. If you have a resistive circuit and you have a source and you're trying to calculate power, then it works, yes. And what I'm going to show you is when we get a couple steps ahead, I'm going to show you a way to calculate the peak value using what's called phasors. Okay, so let's jump back into once we have so once we have the AC value across a resistor in a more complex circuit than this, what values do you use in order to calculate the power delivered to that resistor? We're going to get to that. Okay. Okay. Okay, now this is an introduction to phasors and impedance. So now what I want to do is do another introduction. There's another introduction I have to do here. And I'm going to take you way back in your educational career, a long time ago. Okay, remember number lines? Some point, and I'm sure this was early grade school, we talked about number lines. And exactly why? Well, that was a long time ago. But we said you can represent numbers, and trust me, this is going somewhere. I'm going to take you from number lines to Euler's identity in one whiteboard. And I think it's helpful. Let me draw this over to the left a little bit. So at some point in our grade school educational career, we said, hey, you can represent numbers on a number line, right? And what did that do? That helped us add numbers, right? If you wanted to add 2 plus 1, you started at 1, and you moved over to the right 2 spaces, and 1 plus 2 was 3. And then we introduced at some point negative numbers, right? Freaked us out. And that helped us conceive of, well, what happens if I have 1 and I want to subtract 3? Well, subtraction was just movement to the left by 3, and 1 minus 3 was negative 2. It helped us visualize numbers, right? Instead of looking at these symbols and counting apples and saying, if I add negative 2 apples to 3 apples, what's the result? It helped us visualize in 1 dimension, right? This is 1-dimensional space. What was happening when we added numbers together. And then at some point, trust me, this is going somewhere. So at some point, we added a dimension. We took this X dimension, we appended a Y dimension to it, right? We said, well, this lets us represent numbers with 2 values. So if I had, let's say, an X number 3 and a Y number of 2, you could actually put this on a plot. You could even draw a vector there, right? You could say that I can represent a point, a value in 2D space, right? 2-dimensional space with this concept of X and Y components. And we did stuff like this. We said, okay, that's 3, 2. We'd use pairs of numbers. We separated those numbers into 2 different values. And that's how we identified a value in 2-dimensional space, right? And then we got fancy. We said, well, let's represent this value as a vector starting at the origin. And we use this vector notation, unit vectors. So unit vectors, the X unit vector was a unit, 1, right? A length of 1 along the X-axis. A Y unit vector was a unit along the Y-axis. And we gave them various values. It depends what class you're in, but a recent one I saw was, so 3AX. AX is the unit vector in the X direction. AY hat was a unit vector in the Y direction, right? So this vector describes that point 3, 2, but it does it in an equation. And why did it do it? Well, because you never mix X unit vectors and Y unit vectors, right? When you added vectors together in just this notation up top, you added the X's to the X's and you added the Y's to the Y's, and you never mixed them. And the same thing here. You always added, this was a way to keep unit vector X separate from unit vector Y with coefficients. And then at some point we said, hey, let's go to polar notation, right? So we have this vector V, and maybe it has length A, and then it has some angle theta, right? And then we said, oh, hey, we can represent a point in space that's 3, 2, or 3AX plus 2AY. We can represent that with some magnitude and some angle, right? These variables should start looking familiar. So A at an angle of theta also described that point in 2-dimensional space. And so it didn't matter. A at an angle of theta, whatever that was, you could figure it out from trig, sines, and cosines here, represents a number in 2-dimensional space. 3AX plus 2AY, the same number in 2-dimensional space, same position, or 3, 2. Okay, there's another way, and a very convenient way, it turns out, to represent this, this magnitude and this angle such that it relates to sinusoids. That's where we're going with this. So let me create another axis here. And there's another way that we can separate let's say this 3 from this 2 such that they don't add together when you add a bunch of vectors together. And that way is with complex numbers, right? So if I have a value, let's say that value is 3 plus J2. Okay, let me explain what that means. J is the square root of -1. Okay. The rest of the world, the rest of the, especially physicists, mathematicians, they don't use J, they use I. Okay. We don't use I because we use I for current. So whenever you write down an equation in electrical engineering and you have a complex number, don't use I, it'll confuse you. You'll think it's current and it's not. It's a complex number, it's square root of -1. Okay, so you could write this J2 or 2J, it doesn't matter. I'm used to writing this as J2. It just separates, just like we have a coefficient times AY, this is a coefficient 2 times J. Okay, remember the rules of complex numbers. When you add complex numbers together, you add the reals, you add the imaginaries, you don't mix them together. Just like in two-dimensional space, you add the x's, you add the y's, you don't mix them together. Complex numbers do that for us, okay? I can also plot complex numbers on the complex plane. All right, so a complex plane does this for you. It lets you plot real numbers on the horizontal axis and imaginary numbers on the vertical axis. So for example, this 3 plus J2, 1, 2, 3, 1, 2, would be that location right there. Okay. And these numbers, these complex numbers work just like when you add them together, work just like, 3 comma 2. If I add 4 plus J5, something like that, the result would be 7 plus, that's not a good number, let's do 8. 8 plus J5. I'd get 11 plus J7, right? You add the reals, you add the imaginaries, you get a value. And if I add 2 vectors over here, 3 comma 2 and what was it, 8 comma 5, right? You get 11 comma 7. And same thing if you use the unit vector notation. So my point is, it's a way of keeping X and Y values separate, and it's also a way to represent a magnitude and an angle in polar form, okay? Okay, so let's talk about converting between polar form and rectangular form. Just a minute. So if I have some point in space, and again, I'll just draw a vector to it from the origin. What that does is that helps me write a magnitude A next to that vector and an angle theta. This is the real axis, this is the imaginary axis. Well, given any point, if I have A and theta up from the real axis, I can do the trig on that triangle. And let's see, A, the hypotenuse, times cosine of that angle gives me the leg along the real axis. It gives me this leg right here, the length of that, which is A cos theta. All right, just trig. If I want the imaginary value, right, let's see, I want this, the length of this part of the triangle here, that's going to be JA sine theta, right? The J is there just to separate it from the real value. Okay. Well, great. So what I can say is this, that this point in space in polar notation is A at an angle of theta, right? That's one way to write it. Another way to write this is with, just like up top, this was 3 plus j2, 3 plus j2, that describes that point. It's the real plus j, the imaginary part, a cos theta plus j a sine theta, right? It's describing the same points. So this is a polar notation way of describing this point in space. This is a rectangular notation using j to separate vertical from horizontal. That's in Cartesian coordinates. If you remember Euler's formula, so Euler's formula says E, let's put a coefficient, AE to the j theta equals a cos theta plus j a sine theta. And there's a Maclaurin series. You can prove that. There's a way to prove that. We usually just memorize it. But this is Euler right here. And my point is this: there are 3 ways to describe this point on the complex plane. Polar form, these are both the same over here, rectangular form, or exponential form. And both, or all 3, let you describe a magnitude and an angle. Okay. So the takeaway here is this: know that when you're describing a number in 2-dimensional space, which is also described by a magnitude and an angle, you can use exponential form, you can use polar form, the original form, or Cartesian form. Those numbers all mean the same thing. They all describe a point in 2-dimensional space. Okay, let me bring up a couple slides, and I'm going to make the connection to, well, sinusoids and circuits now. Let's talk about phasors. So right up front, phasors are that vector that starts from the origin and goes out to some point in 2-dimensional space. It's that arrow, it's that vector. We call them phasors when they represent sinusoids. Okay, so I already mentioned that Euler's identity is this. It's actually Euler's equation, Euler's formula is this. It relates a complex exponential to sines and cosines. And this is what I drew. I said if you have some point in space, you can describe it in polar form or Cartesian form using trig. Let's extend this to what a phasor is. Okay, so let me go back, this top formula right here, and I'm just going to take the real part of both sides, right? So all I did is I put real and some brackets around both sides. So both sides of the equation are still equal. Well, what that means is that, let's see, on the right-hand side, the real part of a cos plus j a sine is just the cosine term. Right now, you can see there's some connection here. We're trying to represent a cosine in some way that we can work without it. And kind of a spoiler alert here is this. This is going to let you solve RLC circuits, even so these second order, what normally would be second order circuits, with algebra versus having second order differential equations with a cosine or a sine function in them. Okay, so we're going to take away the need to solve a more complex differential equation by just using algebra and complex numbers. So let me swap this around left for right. So a cos equals, say a cos phi equals the real part of a e to the j phi. Let's make this look more like the equation that I wrote on the board, on the whiteboard. Let's let phi equal omega t plus theta. That was the argument of our cosine term. So now you have on the left exactly what I wrote on the board. This is how we're going to define a sinusoid, some number. I called it Vm, but it's some number times cos omega t plus theta. And that's equal to, based on what we did up top here, the real part of a e to the j omega t plus theta. Okay. Let me show you what the phasor is here and why this helps. So there's just that expression again. You know that when you have a sum, an addition in an exponential, you can break that apart into two products here. So here's the product of e to the j theta, e to the j omega t.
Professor,
Yes.
is the j not like distributive to the omega t and the theta?
Yeah, you know, that should be, actually there should be parentheses up there. So yeah, you're right. There should be parentheses up in there. I don't know why it didn't show up. But yeah, that should be distributed there.
Okay.
And then that's the phasor right there. So the phasor is a e to the j theta. That looks a lot like the exponential form of describing a point in two-dimensional space. What we're going to do is we're going to use that phasor to represent the amplitude and phase of a sinusoid. Okay, so in the time domain on the left, so time domain means you have a t. There's a time term in your equation. It changes with time. In phasor form, or the phasor domain, you have a point in space that represents the magnitude and the phase in one of these three ways, in either exponential, polar, or rectangular, and that's what we were talking about. So when you see these numbers on the right, you can visualize them kind of like you can visualize integers on a number line. You can visualize these terms in two-dimensional space. There's some point on the complex plane. It's described by either Cartesian, right, an x and a y value, horizontal, vertical, a length and an angle, or equivalently, exponential is really a length or a magnitude and an angle. So that's how you should visualize these phasors, as they're a point in two-dimensional space. Okay, why is this useful? Well, let's talk about linear operations on sinusoids and the effect on the phasor that represents those sinusoids. So if I multiply a sinusoid by some constant k, right, in the time domain, it's equivalent to multiplying the phasor by that same value k. So if I'm working with a sinusoid, multiply it by 6, I can multiply the phasor by 6. It's the same effect. If you add time domain sinusoids, it's equivalent to adding phasors. So if I have a1 cos omega t theta 1 plus a2 cos omega t plus theta 2, it's just like adding those phasors together. So if you have a circuit that adds two sinusoids together, you can either add those sinusoids in the time domain or add those sinusoids in phasor form. And so, this is what we do when we do Ohm's law, for example, or we do L di dt. We're multiplying L by some function of I, and that's where this constant comes from. When we're doing some other, when we get to op-amp circuits, you'll see you can add voltages together. We're doing addition, so it's important to know that the effect when you add or multiply by a constant of sinusoids, what happens to the phasors. If you take the derivative, like again, L di dt or C dv dt, we'll get to that. If you take the derivative of a sinusoid, it's like multiplying the phasor by j omega. And the reason is when you take the derivative of what's inside this whole term here, the j omega comes out. When you take the derivative of e to the j omega t, you get a j omega come out. Okay, so taking the derivative in the time domain of a sinusoid is like multiplying by j omega in phasor form. Okay, so here's what this is. So I'm going through this fast. The reason is because The reason I'm showing you this is not because you have to be able to duplicate this and know all of this by heart in order to work circuits problems. But you're going to see this come up. You're going to see me working in the time domain, converting to the phasor form, doing some math, multiplying by a constant, adding things and taking derivatives. You're going to see me doing that in the phasor form and then converting back to the time domain. Okay. All right. So what I'd like to do is so next time what we're going to do is we're going to apply this theory. We're going to just add two sinusoids together. And then we're going to talk about how this applies to resistors, capacitors, and inductors. Okay. All right. Well, it is 6:10 right now, and so let's end class here. Don't forget that homework 4 is not due. Well, it wasn't due today. It's due next Wednesday, so take a look at that on Canvas. Pre-lab 4 is due this Thursday. That's also on Canvas, and then you'll be starting lab 4 on Friday. Check out the Slack workspace. I put a channel out there for this lab and for the homework. So thanks for joining class. I hope it is working out well. Please email me if there's any problem or if there's any way I can make this experience better remotely, and I will try to address it if I can. So I will see you at office hours in about a minute if you would like to join. If not, I'll see you next time.